Today we'll look at some important consequences of conservation laws or conservation principles, which are very fundamental in the study of motion itself. These principles have a long history, but we've understood very carefully where they come from, what their limitations are and what their consequences are at some level, and I'd like to explain how these things are consistent with Newton's laws and how they indeed support and corroborate these laws and help us solve problems in dynamics. Now, you're already familiar with these terms such as conservation of energy, conservation of linear momentum, conservation of angular momentum, and so on. But it turns out these principles are saying something very fundamental about space and time themselves, and we will see how these principles come about, at least qualitatively. Now, Newton's first law, which says that a body that is at rest or in a state of uniform motion in a straight line will continue in this state of motion or state of rest unless acted upon by an external force. This law already has in it a potential conservation law, because it essentially says, the first law essentially says that the rate of change of the momentum is equal to 0 unless there is a force acting on the body. And that's the reason why it continues in the state of uniform motion, because it essentially says that this will imply that P is equal to a constant vector, of course. And we say it's a constant of the motion, which I'll often abbreviate as COM, and this is a conservation principle. So it says that the momentum, once you specify it at some initial instant of time, continues to be the same for all time unless there is an external force acting on the body. So if this is the momentum at t equal to 0, that remains the momentum for all time as the body moves. So the position changes, but the momentum does not change, and that's a conservation law. It says the momentum of this object is conserved both in magnitude as well as direction. So already you can see that the first law is essentially saying that there is a certain quantity, a dynamical quantity, which doesn't change as time goes along, even though other quantities such as the position would change. Now, the second law is completely consistent with the first law, and the second law says that in an inertial frame, dp over dt, the rate of change of momentum of the body, is equal to the force acting on the body, the net force acting on the body for a single body. Now, this law is consistent with this law because it says if f is 0, then p is a constant of the motion. So it's completely consistent, but you mustn't imagine, as is sometimes done, that the first law of motion is a consequence of the second law. Not at all. The first law of motion essentially helps you to define an inertial frame, and the second law says that in these inertial frames, the rate of change of momentum is equal to f. And of course, when f is 0, happens to be 0, then p is a constant of the motion. So the second law is completely consistent with the first law, but the fact that it applies in inertial frames and the first law essentially helps to define an inertial frame means that these two laws are independent of each other, even though it looks as if the second law is a more general case than the first law. Whatever. So there's a constant of motion in the absence of an external force. Now, the third law carries this one step further, and this was entirely Newton's contribution. The first law essentially was known to Galileo, and the second law was around at that time, but the third law is entirely Newton's creation. And what he said was that if you have two bodies in interaction with each other, and these two bodies or objects or masses 1 and 2 in interaction with each other, then the rate of change of momentum of the first by Newton's second law is equal to the force acting on the first body, and the rate of change of momentum of the second is the net force acting on the second body. Now, the forces acting on these bodies could arise from a large number of reasons. So here's body 1 and here is body 2, and let's suppose they exert a force on each other, and in addition there is some other force as well acting on both these bodies. So this is equal to F12. By this I mean the force on body 1 by body 2 due to body 2 plus any other force which is acting on 1, and let's call it some external force due to some agent other than body 2. And similarly, this is equal to F21, which is the force exerted on body 2 by body 1 plus F2 external, the force acting on body 2 due to any other agency. Then simply by adding these two equations, you immediately see that d over dt P1 plus P2, which is the rate of change of the total momentum, let's call that capital P, where capital P is just P1 plus P2. This is equal to F12 plus F21 plus F1 external plus F2 external. That's just by adding the two equations. Now Newton's third law says that if there is no external force, if this term should happens to be 0, then and only then this momentum is constant. So it's equivalent to saying that action and reaction are equal and opposite. So the statement is, the dynamic statement is F12 is equal to minus F21. So what does that mean? So the third law says F12 shall be equal to minus F21. In other words, the magnitudes of these vectors are the same, but they are oppositely directed. So if F12 looks like this, then the vector F21 is in the opposite direction, F21, with the same magnitude. Okay. And this is the content of Newton's third law. But immediately, as a consequence, it follows that dP over dt equal to d over dt P1 plus P2, by definition this quantity, is equal to 0 if F external equal to 0. In other words, if you have a system of two bodies, here's the system, and there's no external force on this system except the forces on 1 and 2 due to each other, then by Newton's third law, since action and reaction are equal and opposite, F12 is minus F21 implies that the sum of the momenta of 1 and 2 is a constant of the motion. So this implies that P equal to a constant of the motion for two bodies. Now of course it still remains to ask, can we say something more? Under what conditions is this going to be true? Are there cases where it's not true? It will turn out as we go along that under a very wide variety of circumstances, this is indeed true, this relation is true, and this is indeed a constant of the motion, provided there is no external force acting on these two bodies. Okay. This includes the force due to other particles that may be present in the universe. When all of those are gone, and you look at only these two particles, then the total momentum is a constant of the motion. Okay. And that can be a good approximation in many cases, as we will see. So the constancy of a quantity arises when its time derivative is identically 0, and you can now see that both the first law and the third law actually yield constants of the motion. They are saying something about constants of the motion. Now what's the meaning of these constants of the motion? What's the significance? Well, we already saw that in principle when you integrate Newton's equations of motion, you need integration constants which are determined by the initial conditions. So every time you discover a constant of the motion, you have gone a step further in integrating and finding explicit solutions of the equations of motion. So that's the reason for the importance of constants of the motion, and we will harp a lot more on this as we go along. When we see an application, you will see immediately the role played by the important role played by these constants of the motion. What happens if you have more than two bodies? And that's a generalization that follows again from the third law, and it goes as follows. So let's suppose you have n particles or n masses. We don't care what these masses are in general, m1, m2, m3 up to m sub n, and you have equations of motion for each of them. So dp1 over dt is equal to, and now let's suppose that there is no external force on these particles except what they apply on each other. So this is equal to F1, the total force on body 1, which comes due to body 2, due to body 3, 1n, due to the body n, and similarly dp2 over dt is equal to F2, which is equal to F21, the force on body 2 due to body 1, plus F23 dot 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 plus F2n, and so on all the way up to the nth particle whose equation of motion, this is equal to F sub n, this is Fn1 plus all the way up to Fn n minus 1. There is no self interaction, obviously. Each body sees forces due to the other particles or the other bodies, and that's the set of equations. And we add them all up and use Newton's third law. And the result therefore is d over dt p, which is equal to d over dt p1 up to Pn. This is the total linear momentum, of all the particles added up vectorially. This quantity is equal to, on the right hand side, F12 plus F21, F13 plus F31, and so on. So this breaks up into pairs which goes like F12 plus F21 plus F13 plus F31 plus etc., right up to plus Fn minus 1n plus Fn n minus 1. All the terms, n squared terms, add up and break up in pairs, and then it immediately tells you that by Newton's third law, this is equal to 0, this is equal to 0, this is equal to 0, which implies that P equal to constant of the motion. So it says that if you have a collection of particles in this fashion and they're interacting with each other, I call that a system. The total momentum of the system is a constant of the motion unless there's some external force acting on the system as a whole. But as long as they're seeing forces, each of the bodies is seeing a force due to the other bodies in this system, and only that, and Newton's third law is applicable, then the total momentum of the system is a constant of the motion. It's important for you to understand that in this situation, P1 plus P2 is not a constant of the motion. So what's being said is that for each pair of objects, particles, Fij is equal to Fji with a minus sign vectorially for each I and j, I not equal to j. There is no self interaction involved here. While that is true, it is not true that for a given pair Pi plus Pj not a COM in general. So the sum of the momenta of any two particles in the system is not a constant of the motion. That's because each of the momenta is changing due to many forces. As long as all these were absent and you had just two bodies and this was equal to minus that, then the sum of the two momenta was a constant of the motion. But the moment you have other forces on the system due to particle 3, 4, 5, etc., then the sum of any two momenta is not a constant of the motion, but this still remains a constant of the motion. This quantity here, the total momentum, is still a constant of the motion. Okay. So this is a consequence of the fact that there is no external force on the system. Now where does this law of conservation of momentum come from? Well, by the way, this fact that it's the total momentum that's a constant and not individual pairs of momenta also says something about the limitations of the conservation principles. It's not giving you all the information about the system, but it's giving an overall constraint on the system, and that's a useful piece of knowledge to have. Now where does this whole thing come from? What's the origin of the law of conservation of momentum in these situations? The answer lies a little deeper in mechanics, and we will not go into that here, but I'll state the answer in words. The answer has to do with the fact that empty space is regarded as homogeneous. So the fact that you could take this system and the same thing could be shifted to some other location in space without changing anything else, and the physics of what's going on in it will not change if there is no overall external force on the system as a whole, which will break this invariance, this translation invariance as we call it. The shift of any location does not change the properties of the system, and this shift, the fact that things do not change under a shift of the origin of coordinates, for instance, is what is ultimately responsible for the conservation of momentum, linear momentum, as long as the conditions are right. As long as you have the statement that there is no external force on net external force on the system, and the system only sees forces due to the different components of the system acting on each other, pairwise they cancel out due to Newton's third law, and then you are left with the conservation of total momentum. So this is an important idea that, let me write this down. Conservation of momentum of linear arises from the homogeneity of empty space. When you have nothing going on in this space, then we believe that space is exactly the same at different points in space. Nothing changes. But then the presence of external forces, the presence of fields and so on will break this homogeneity. And here's a simple example to show how. You're familiar with the fact that in projectile motion, when you have gravity acting downwards, there's an acceleration due to gravity which is minus g times the unit vector in the y direction. This is y and that's x. If I project a projectile from here, from the origin in this fashion along this velocity vector, this moves in a parabolic path and falls down there. Exactly the same thing would happen if I projected it from here with exactly the same initial velocity. It would be a trajectory of this kind, and so on. It's easy to see that apart from a shift in the coordinates, whatever is going on here is the same as what's going on here is what's going on here. So in the horizontal direction, there is complete spatial homogeneity, and that's why in this problem it turns out that the x component of this momentum of this projectile is a constant of the motion. The y component is not, because there's a force in the y direction. There's gravity acting downwards in the y direction given by this, and because of that what happens here is different from what happens here is different from what happens here, as you can see. And this is entirely a consequence of the fact that translational invariance in the vertical direction is broken by the fact that you have a field in the vertical direction. You have a gravitational field. And this is true even if the field is exactly the same at all points. Within this approximation, it's clear that the gravity here and the gravity here and the gravity here, the force is exactly the same. So even though the force is the same, the existence of this force is enough to cause the momentum in the y direction to change, because it says dpy over dt is the vertical component of the force, and that's not 0. So the moment you have a force in this direction, the translational invariance of this direction is broken and you have no conservation of that momentum. So py is not a constant of the motion, but px is. Exactly as saying that this piece of chalk, as far as this plane, the xy plane is concerned, if the vertical direction is the z direction, there is translational invariance in the xy plane. There is no force in the x or y directions. Only gravity acts, and that acts in the vertical direction. So the translational symmetry is broken in the vertical direction and retained in the horizontal directions, which is why no matter how I launch it, this projectile, the horizontal component of its momentum is going to be a constant of the motion. If I do it in the xy plane, xz plane, then the x component. If I do it in somewhere in between the x and y directions, then of course the horizontal component, whatever it be, will be a constant of the motion. So this is important to understand, that not only do you have a conservation principle, we also know where it comes from. It comes from the fact that empty space by itself is taken to be homogeneous, have the same properties at all locations. And that's the reason for the conservation of linear momentum, provided the circumstances are right. And this is an important point to understand. In the same projectile problem, you could ask, what happens if I have the full problem of gravitation occurring due to the center force of gravity from the earth, and the field lines of the gravitational field not taken to be parallel lines pointing downwards of constant magnitude, but we take it to be the full inverse square law of gravitation? What would happen then? Well, in that case it's very clear, if you have distances which are comparable to the radius of the earth, then it's very clear that the motion is not in a parabola of this kind. The motion is actually part of an elliptic orbit, and then it is certainly true that you don't have this conservation in either of the two directions. And we will see this in a minute when we talk about conservation of angular momentum. Okay. So much for the origin of the linear momentum conservation. We will use the conservation of linear momentum very shortly when I talk about an important application to what happens when two bodies collide and separate and go their own way. And we will see that to a good extent the conservation of linear momentum and the conservation of energy will together help us solve this problem to a great extent without knowing the details of what happens during the collision. Okay. Now what about angular momentum, conservation of angular momentum? Where does that come from? Well, let's go back and look at what happens to Newton's law for a single body, which was dp over dt equal to the force on one body. So we are going to talk about the rotational analog of the second law. As before, I start with a single particle, single object, and say the rate of change of its momentum is the force acting on it. And now I'm interested in the so-called orbital angular momentum, L. This is the orbital of the body about the origin of coordinates, whatever that origin be, and this has a formula which is r cross p. So it's perpendicular to r, the instantaneous position of the particle, perpendicular to p, the instantaneous momentum of the particle, and it's in a plane directed in the plane along the direction normal to the plane formed by r and p. And the magnitude is the magnitude of r, magnitude of p times the magnitude of the sine of the angle between them. Okay. Now what about dl over dt. So let's multiply this, let's differentiate this. Dl over dt is equal to dr over dt cross p plus r cross dp over dt. So the same chain rule of differentiation applies whether you have a dot product or a cross product or you have vectors, it doesn't matter, the same rule applies. So we have this cross plus that. I should write it like this. Okay. But in the cases we are looking at, this quantity is the velocity by definition, and in the cases we are looking at, it's the momentum divided by the mass. So essentially P equal to mv equal to m dr over dt, and what we have here is a situation where dr over dt, the vector, the velocity, cross product with itself, but the cross product of a vector with itself is 0 because the angle between the two vectors is 0, and therefore this term is identically 0, and you are left with r cross dp over dt, but that is equal to r cross the force on the body by the second law of motion, and this is what you call the torque. Okay. So we have the rotational analog of Newton's equation of motion, second law, for a single body. It says the rate of change of its orbital angular momentum is equal to the torque on the body, r cross f, the moment of the force about the origin, and therefore as in the case of the second law, L is a constant of the motion if the torque on the body is 0. So we have a conservation principle which says that if the torque on a body is 0, then its angular momentum does not change. This is the exact rotational analog of the law for linear momentum in this case. But we can go a little further, and we will do that next when we consider a set of bodies and ask what happens when you have the third law operating and you have a collection of particles, and we will do this, we will take this up in the immediate future.